Welcome to our today's class. We talk about the motion of a body inside a lift. This is a section under Newton's laws of motion. We have described the three laws. The first one we talked about the inertial force. The second one we talked about the net force that causes acceleration. The third law we talked about the action and the reaction. So let us see how we can apply these three laws to describe the motion of an object that is inside a lift. We have a cartoon here, which is a person that is inside a lift and on a weighing machine. This machine here is going to give us the weight of that person inside there. One thing that you must note is that the weighing machine in this case is going to read the apparent weight, okay? And this weight is always equal to the reaction of the surface. So the first case that we have here is for a lift that is not moving, that is at rest. And we can describe that easily if we consider an object that is placed on a surface. We know that the weight is always pointing downwards, and because of the surface, there will be a reaction that is upwards. So this is a reaction. So if the body is not moving, what is the relationship between the weight and the reaction? Newton's third law. The two will be equal. So we shall find that the action and reaction are equal. That means the weight of this body, what we call the rest weight, or the actual weight of that body, is equal to the reaction for this body to be at rest at that given surface. And if the two forces are equal, there is no net force. The net force is zero. So what will be the reading on that given machine? You find that the reaction is equal to the actual weight, and we have already said that the reading will be the reaction by the surface. So the weighing machine for this given situation is going to read the actual weight of that given person. Now suppose the lift is accelerating upwards. If the body is accelerating upwards, it means that we now use Newton's second law to describe the situation. And the Newton's second law will tell us that if there is an upward acceleration, there must be a net upward force. So in this same situation, we have two forces, the usual ones, that is the weight and the reaction. Now again, we are saying that here there must be a net upward force. Now this net upward force here is equal to the mass of the person times the acceleration, A. And for us to get a net upward force, it means that the upward forces must be greater than the downward forces. And in this situation here, we see that the reaction here must be greater than the weight. So We have three terms here. We have the weight, we have the reaction, and there is a net upward force. If we relate the three, we are going to find that the net upward force is equal to the surface reaction. These two are in the same direction, so we take them as positive. Then minus the weight, which is in the opposite direction. And if we make the reaction subject, that means we are taking reaction to this side and MA to this other side here. We are going to arrive at this relation here. So the reaction due to the surface is equal to the actual weight. We have the actual weight here, plus another term, which is the net force. And we have already said that our weighing machine is going to read the reaction. So in this case, you can see the reaction is equal to the actual weight plus a net force. And that tells you that this object will be heavier than it actually is. And so the reading on that weighing machine will be greater than the actual weight of the person. And this is the relation that we can use to calculate that. Now, suppose suppose the lift is moving downwards with an acceleration here. If the lift is accelerating downwards, that tells us something, that there must be a net downward force. So this force here is not now moving upwards. This force is directed downwards. It's a net downward force causing causing an acceleration in the downward direction. So that again will tell us that this relation will not look like this. This relation will be different. For us to get a net downward force, weight or the downward forces must be greater than the upward forces. So the weight here is greater than the reaction. So now if we combine these three in an equation, you'll find that the net downward force, which is given by mass times the acceleration, is equal to the weight. If you look at it, you'll find that these two are in the same direction. We have the weight in this direction, we have the net force in this direction. So these two must be written with the same sign. Then minus the surface reaction, which is the only force that is in the opposite direction. And as we have done before, you make the reaction subject of the formula, means you are bringing the reaction on this side, you are bringing M here on this side. This is going here, and this one on the other side here. So you are going to arrive to this relation here, which is the reaction. And we have already said that our weighing machine reads a value that is equal to the reaction. That is, the apparent weight is equal to the reaction. So this will be the apparent weight or the reading on that weighing machine. So in summary, we have seen that if the lift is at rest, the reading on the weighing machine will be the rest weight. If it is moving upward with an acceleration here, the reading will be the actual weight plus the net force. And if it is accelerating downwards, the reading will be the actual weight